So welcome to day 2 of properties of logarithms. Hopefully by now you feel very comfortable with the first few properties that we've learned about logarithms, and so you're ready to move on and learn some more. Well, we talked about the exponential and logarithmic operations. They sort of undo each other since they're inverses. They're just really other ways to write the same equations or expressions. Logarithm is just another way to write an exponent, but just in a different form. So that it sort of undoes it, puts it in a different form. So they're inverses. And so these next properties are the inverse properties. In some ways, these properties are really sort of unnecessary if you really understand about how logarithms work and how to switch from logarithmic to exponential form and vice versa, and if you know the other properties. But these are still properties, so we're going to introduce them, but just know they're not really ones that you would have to necessarily commit to memory, because you can sort of, still kind of get around without applying these by just knowing what you know about logarithms. So the first one is the log base b of b to the x power equals x. So now, what that's basically saying is if the base of the logarithm and the base of your result are the same, that the exponent on the result is the value of the logarithm. Well, that kind of sounds confusing, right? And so really, if you just use that power rule that we just talked about, you really don't need to know this property, because if I were to take this log base b of b to the x power equals x, if I were to actually take this and use that product property on it, I would bring that x down in front. I would rewrite it like this: the x times the log base b of b, and if the base is b and the result is b, then the power must have been 1, and so that it turns out that that's really x times 1, which is x, and that's exactly what that property says is true. So like, for instance, with this next one, if I had say I didn't know the value, I wanted to find the value of the log base 10 of 10 to the 7th power, what I would really be saying is what would I have to raise 10 to get 10 to the 7th power? Well, that's sort of obvious. We'd obviously have to be raising 10 to the 7th power. And so I can kind of think about it like that, or I could simply think about it like this. I could take that 7 down in front. It'd be 7 times the log base 10 of 10, and I know that if the base and the result are the same, the power must be 1, because 10 to the first must be 10, and so then I could see that that's 7 times 1, or just 7. And that's exactly what that said right here. It said that the value was 7. Now this next property can also be very confusing, but again, it's not a necessary property that you have to know, because you can use other properties in place of it. And basically, if I had to explain what this statement in the red box says, it's saying if you have a base that's raised to an exponent with a logarithm of the same base, then whatever the result is of that logarithm will be the value of the exponent. And I don't know about you, but that sounded very confusing. And so what I do is, again, I think about it using other properties. I think about, well, if I converted this over to a logarithm, which we just spent the last lesson learning how to do that, and we did that, it would look like this. So we'd say log, and then we figure out what the base is, and then we figure out what the exponent is and the result. So the log base, well, the base of this expression that we have here is b. It's a log base b, right? And the exponent is this piece right here. That's the exponent that it's being raised to. So that actually has to go on the other side. And so then I know that the result is x. And so that's this part right here. And that's got to go right there. And so basically it says the log base b of x is equal to the log base b of x. That's sort of what that statement is saying. And so what it does is, again, it provides you a way of kind of getting around having to know that property. And so I'll look at an example to demonstrate that here. Okay, so let's say you wanted to simplify 10 to the power of log base 10 of 2, and you wanted to know what the value was. So let's say you didn't know that this was 2, say this wasn't here, and you wanted to know what the value of that was. Well, you could simply say, well, I'm trying to figure out what this is what I don't know. This is, say we call this, just a question mark or an X. And so if we were to convert this over to log form, we'd say, okay, log, and the base is 10, and this is the exponent right here, so this goes on the other side. So we'd write log base 10 of 2. And so what we're really trying to find out is, what is this? And so we can tell by just looking at the other side, it has to be 2. Right? So we could answer this question and find out that log, or 10 to the log base 10 of 2 is 2 by just using our other log properties and switching from exponential form to log form. All right, let's go ahead and turn the page. So let's take a look at a few examples of recognizing inverses. So example A wants me to simplify the expression, and it's log base 3 of 3 to the 11th. Okay, so what I know what that means is that I want to know what power I have to raise 3 to get 3 to the 11th. Well, hopefully that's pretty clear that that has to be 11. But we could use that power rule that we talked about, and we could bring that 11 down in front and rewrite it as 11 times the log base 3 of 3. And remember, if the base and the result are the same, then the value of that logarithm has to be 1. So this really means 11 times 1, or 11. And that's where that came from. It's another way to look at it. What about B? Log base 3 of 81. Well, that one, you know, really just you're thinking about what power would you have to raise 3 to get 81. And so I'm trying to fill in the blank. What exponent? Well, 3 to the 4th power is 81. So the answer to this would have to be 4. Now I should probably clarify C, what that's actually saying, because with that, you know, sometimes the equation writer, it's kind of difficult to get this to look exactly the way we want it to look. But this is supposed to say 5 raised to the log base 5 of 10 power. And so I think about right away about, this looks kind of confusing, so I want to switch this over to logarithmic form. So when I think logarithmic form, I think log, and then the base, well, the base of this exponent is 5. And then I'm trying to figure out the result. This is what I want to know. And I know the power, so the power goes on the other side, or the exponent goes on the other side. Log base 5 of 10. And so now I can just look at the two sides and see, well, what's missing here? Well, what must be missing to make this the same thing on one side as it is the other is 10. And so I know that that means that the answer to this, that the 5 raised to the log base 5 of 10 power is actually 10. So if you know that property and you can kind of commit that to memory, you could have looked at that and you could see that, oh, hey, you know, these are the base and the base of the logarithm are the same. They sort of essentially just cancel each other out and leaves us with that 10. So if you want to think about it using that property, or if you just want to use other properties so that you don't have to remember that one, either way you're going to get the same answer. So how about we give D and E a try as a you-try question. So using some of the examples that we've done, take a look at each one of those, D and E, and see if you can find the value to the expression. So pause the video now. All right, so your answer should be 0.9 for D and 8x for E. So one of the reasons why we're learning all of these properties of logarithms is we don't often have the aid of our calculator to help us evaluate logarithms. So these properties kind of help us to do what, you know, to kind of work with some of these logarithms that we can't use our calculator to evaluate. Now you may remember that we talked about the common log. Now the common log is base 10 log, and your calculator can only compute logs in base 10, that's the common log, and another one we'll talk about in a later lesson, which is base E. That's called the natural log. This next property we're going to talk about is actually my favorite logarithm property, and it allows us to kind of get around the fact that our calculator will only do log base 10, and we can use this new property to help us to do what's called changing the base. So what the change of base property says is this. The log base b of x is equal to the log base a of x over the log base a of b, where a can be any value that you want. This base that we change to, we can pick anything that we want. So that's what a represents. You may choose any value that you want the base to be. So what that change of base property says is this. You can change the log of any value to the log base whatever, say 10 to whatever, of the result. So this value here goes on the top, divided by the log base a of the original base before you changed it. Now that might sound a little bit complicated, but once you see an example of this done, I think you'll see how the change of base property is really, really helpful. And so we're going to do this next example, example 5, in 2 different ways to show you how you can change the base of a logarithm to anything that you want. So first of all, we're going to be evaluating in both different cases the log base 32 of 8. So if we think about what the question's asking, they want to know the exponent that 32 would have to be raised to get 8. Okay, so clearly it's going to be something less than 1 because, you know, 32 to the first is 32, but we need to get it to be 8. So we're looking for the exponent to raise 32 to get 8. So if we wanted to use a base 10, which would then allow us to use our calculator, what the change of base property says is that log base 32 of 8 could be equal to the log base 10 of 8 divided by the log base 10 of 32. So what's the advantage of that? Well, the advantage of that is now we can use a calculator to do this. And we can actually type in log base 10 of 8 divided by log base 10 of 32 into our calculator, and it will give us the exponent that 32 will have to be raised to get 8. And it turns out that the calculator says it's 0.6. Now, I never would have guessed that. So this allows us to evaluate something that we may not be able to do in any other way by changing the base to something that we can work with. In this case, the common log, which allows us to use the calculator. So if you were to go back and check and you raised 32 to the 0.6 power in your calculator, you would see that it equals 8, and so that checks. Now another way we could do this is to choose a different base. Like let's say we chose base 2. Now why would I choose base 2? Well, when I think about 8 and 32, those are both powers of 2. So maybe it would be helpful if we were working in base 2. So let's say we wanted to change this log base 32 of 8 into base 2. Well, then that would look like this. Log base 2 of 8 divided by log base 2 of 32. Well, the power that I'd have to raise 2 to get 8, well, that's pretty easy. That's 3 because 2 to the third power is 2 times 2 times 2, and that's 8. And when we think about 32, now you might know that as a common power of 2 also. That actually is 2 to the fifth power. So if you multiply 2 by itself by 5 times, well, you already saw if we multiplied by itself 3 times, we got to 8. Then by 2 again, that's 16. By 2 again, that's 32. So 2 to the fifth power would give us 32. And so that 3/5 is really the same thing as 0.6. And so we're getting the same thing, but just using 2 different bases to evaluate the same logarithm. So when you do change a base, you can change it to any base that you want. Let's go ahead and turn the page and look at a few more examples. So how about log base 9 of 27? Let's look at how we could do that by changing it to base 10. So if I changed it to base 10, it would be log base 9 of 27 would be equal to the log base 10. You don't have to write the subscript 10. You can just write it as log 27 if you wanted to, but I just am reminding you that if that's base 10, divided by the log base 10 of 9. And now I can just go straight to my calculator. I type in log of 27 divided by the log of 9, and it tells me it's 1.5, or if I wanted to write it as a fraction, that would be 3/2. So I know that if I were to raise 9 to the 1.5 power, and we can check it, if I raise 9 to the 1.5 power, we actually will get 27. And you think about, that's if we instead wrote that as a fraction. So it was 9 to the 3/2. Remember that the fractional exponent means that there's a root and a power at the same time. So what this really means is it's a square root of 9 cubed, which the square root of 9 is 3, and if we raise 3 to the 3rd power, we would get 27. So that makes sense that that is the correct answer. Now another way to do this is I could instead, and remember, you don't have to do both ways, just pick a way in each problem and which makes most sense to you. But I could change to base 3 instead. And the reason why I would pick 3 is both 9 and 27 are powers of 3. So I could write the log base 9 of 27 as the log base 3 of 27 divided by the log base 3 of 9. And then the log base 3 of 27 means 3 to what power is 27, and that's 3. And log base 3 of 9 means 3 to what power is 9, and that would be 2. And so I get that 3/2 again, just using a different base. So we're going to make this one a you-try question. And I'm going to really actually allow you to pick either way. This one says to choose base 2. So, method 2, if I use method 2, I would change to base 2, and the reason why is both 8 and 16 are powers of 2. So if you want to use method 2 and try it that way, that's great. And also you might consider trying log base 10 and then use your calculator. But I want you to pause the video now and evaluate log base 8 of 16 using one of the methods, or both. All right, so how did you do on that one? If you use the calculator, you probably got the repeating decimal 1.3 repeating, which then you can have the calculator convert to a fraction, which is really preferable to have the fraction just by hitting the math and the fraction key. Now, if you did this using base 2, you would have gotten 4/3 directly. Now, our final example, we're going to be looking at a geology application with logarithms. So logarithmic scales are useful for measuring quantities that have a very wide range of values, such as intensity or loudness of sound, that's the decibel scale, or energy released by an earthquake, and they use the Richter scale. At least in the past they did. They use a more updated scale nowadays with the new technology. So we're going to be looking at an application that's related to the tsunami that occurred in December of 2004. So the tsunami in December 2004 was started by an earthquake with a magnitude of 9.3. And the question is, how many times as much energy did this earthquake release compared to the 6.9 magnitude earthquake that struck San Francisco in 1989. Now you may remember that earthquake in 1989. I mean, you might not remember because you probably weren't around, but if you've ever heard about that, that actually occurred right before one of the World Series games with the San Francisco Giants. So that was a 6.9 magnitude, and that was a pretty significant one in the history of our country. But there was this one that was 9.3 in magnitude that caused the tsunami in 2004. And what we want to know is how many times more energy was released. Just another quick note on that. That tsunami in 2004, remember that was in Thailand, and I believe that up to now is the deadliest tsunami in history, although I'm not quite sure. There was one also that happened in Japan a few years back, so I'm not positive which one was more severe. Now the formula that we use to calculate the magnitude of an earthquake as it relates to the energy released is m is equal to 2/3 times the log of the quotient of the E, which is the energy released, divided by 10 to the 11.8 power. So what we're going to need to do is use this formula to calculate the energy for magnitude 9.3 and a magnitude 6.9, and then we'll compare them. So that's the first thing we're going to do is we're going to have to take and plug 9.3 in for the magnitude first, and we'll see what the energy released, and then we can do the same thing for the 6.9. So I would plug in 9.3 for M. 9.3 is equal to 2/3 times the log of E over 10 to the 11.8 power. Now the first thing I would want to do if I wanted to solve for E, that means I've got to get E all by itself, but it's got all this other stuff with it, is I might want to first get rid of this 2/3. So if I wanted to get rid of 2/3 that's being multiplied by this log, I could multiply both sides by the reciprocal, which is 3/2. So if I multiplied both sides by 3/2, that would just cancel out the 2/3 over here, which makes that much less complicated looking. And on this other side, the 9.3 times the 3/2 would give me 13.95. And now that's equal to the log of E divided by 10 to the 11.8 power. Now notice that this logarithm does not have a base listed, and that's because this is base 10. So at this point, what we could do is we could switch this over to exponential form by taking the base of 10, raising it to the power, which is this 13.95, and setting it equal to this result. So that's what 10 to the 13.95 should equal, is the E over 10 to the 11.8. And so if we did that, this is what it would look like. It would be 10, which is our base, to the 13.95 power is equal to E, which is the energy, over 10 to the 11.8 power. And now all I have to do is put this 10 to the 13.95 power over 1, and we've got a proportion. And we can solve that just using the cross products. And so when I do the cross products, the 1 times E is E, and the 10 to the 13.95 times the 10 to the 11.8, well, when bases are the same, you just add the exponents. If I added those exponents, I would get 10 to the 25.75 power, which is a very, very large number. And that just came from adding the 13.95 and the 11.8. And so that's the energy that's released by the 9.3 magnitude earthquake. So now let's do the exact same thing for the 6.9. So we'll start off writing out by plugging in 6.9. So it would look like this: 6.9 equals 2/3 times the log of E over 10 to the 11.8 power. And then we can try to solve for E again. So this time we're going to multiply by 3/2 again to get rid of that 2/3. And when I multiply 6.9 by 3.2, I get 10.35. And now that's equal to the log of E over 10 to the 11.8 power. Now since this is a base 10 log over here, I can now go to exponential form. In other words, convert it over by starting at the base, raising it to the power, and it will have to equal this result. So base is 10, 10 to the 10.35 power equals E over 10 to the 11.8 power. Well, I can turn that into a proportion by putting that over 1, do the cross products again, and I get E is equal to 10 to the 22.15 power. And again, I just got that by adding the 10.35, that exponent, and the 11.8, because when the bases are the same, you add the exponents. Now the final step is we have to compare these two things. We have to see how many times greater the 9.3 is than the 6.9. So we're going to compare this 10 to the 25.75 power to the 10 to the 22.15 power. And of course we'd have to use our calculator to do that, which turns out to be about 3,981, or about 4,000 times more severe and or more energy is emitted from the 9.3 magnitude than the 6.9. Now the significance of that amount, 4,000 times as much energy, would probably have been felt even in a stronger way if that had not taken place out in the middle of the ocean. Now the secondary results were that tsunami that caused that, the energy released out in the ocean caused that incredible tsunami it killed many people, but maybe not anywhere near in comparison to how many might have lost their lives and how much damage could have been done if that earthquake was actually done on land. So, well, that does it for today's lesson. And we're going to be looking at, for the rest of this chapter, many more applications of logarithms and using different strategies to solve logarithms to answer real life questions. So, thanks for coming to class.